is Yiwei Kang. My topic is Max RetinaXNet, a power-efficient image enhancement with maximum intensity preservation. Okay, I have no scripts, so I have to talk in my person. Yeah, okay. My outline is like this. First, I will explain my motivation to do this, and second, I will explain the background of this research. And the third is my proposed method, and I will show you the result and experiment approach. And finally, the comparison and conclusion. This is why I do this research. Yeah, okay. In the past 2 years, I was a VR developer engineer, and I do some applications for my international clients. So I know such things that in this realm, the bottleneck or the challenges in VR headsets is the brightness of the display. That if you are wearing a headset on your own and you keep watching this video or something like that, you will feel dizziness and you will get uncomfortable if you turn the light so bright. Yes. So I'm wondering how to deal with this kind of situation. That if we can enhance this resolution or not resolution, enhance the image quality to reduce the brightness or the illumination, then we can display the same quality of the image but with lower brightness. By the way, ESG is the popular topic these years. So if you can reduce your footprint of the carbon, then you can get a higher enterprise value. Yes. So all these things push me to do such topic. Okay. So let me illustrate this situation. Okay. So the scenario is like this one. The left-hand side is the original quality, and once if we can enhance the quality with this one, then you can get a better result, the same result with lower brightness level. Okay, so this is what I'm going to do. What I'm going to do is to enhance the image of the quality of the image without enhancing the exposure. Okay. So let's guess which one is the enhanced one. Professor, which one is the enhanced one?
Right.
The right one, right?
Like this.
Okay, no, the left one.
Okay.
Yeah, it says 8.8 total or average power consumption that displayed with little change with, oh, the camera is pulled down. Okay, with little change in these pictures. Also, it can apply to the lower one or the darker one, that it can save more energy with the same with better result. Okay. Okay, so let me explain the background of the research and the detail of the research. The first thing I want to explain is the low light image enhancement. That is techniques to improve our the low light images with enhanced exposure, contrast, or some edge detection or these features. And the challenge is that there are too many noise in the dark images. So if you enhance this image directly, you will amplify the noise of the image like that. Or someone will smooth the image with Gaussian blur or something like that. Then you will get over smoothing if you directly do like that. Yes. Okay. Another approach is to apply some exposure level to enhance the brightness of the image. But you can see it's not so realistic. So you will feel it's too bright or too bright. Okay. So there are many approaches proposed to address this problem. The simplest one or the classic one is the histogram equalization. It's a classic algorithm to stretch the bandwidth or the bandwidth of the light so that you can get an overall average of the light. Yeah, so you can see the two images illustrate the concept. But you can see if we apply this method, then there are so many noise amplified, so you will feel uncomfortable or unrealistic. So the second one is proposed, that is gamma correction. This method is widely used nowadays in filming or photography, so that you can increase the exposure to the lower region of in the image, and you won't overexposure the brightness in those brighter regions. Yes. Okay. The after one is simply apply the gamma correction directly to the dark one. Yes. But if you try to do the histogram equalization, then the gamma correction, the better result will get. Oh, it's got. Okay. The second one, the advanced one, is retinics, which is the combination of retina and the cortex. This theory states that one image is composed by two elements. The first is the reflectance of the obstacles that it reflects the light. Yeah. And another one is the illuminance from the resource, from the source light. So later on we will explain the detail of this. Yes. Okay. It shows that the source image I can be treated as the element-wise product of the illuminance L and the reflectance R. And we usually predict the illuminance first, then divide by the illuminance, then get the R, the reflectance. Yes. Okay, so this is what you will get if we apply this theory. So in these days, deep learning improves those skills a lot. So many popular framework or some network are proposed to increase the precision or the quality of the image with this kind of structure. This is the structure of Retinics net, proposed in 2018. Yeah, 2018. So my net is similar to this but improved because this kind of networks won't deal with this image enhancement in such a short time that you can be a part of the application of your VR headset or smartphone. Yeah. And you can see much difference. Yeah, it's almost the best one. This is a new math approach published in 2022. Yes, very clear and there's no such noise in the picture. Yes. And there are a lot of other approaches to address this such problem, the low light image enhancement. But you can see a common in their approaches is they always exposure or increase the brightness of the images to get the higher PSNR or the intensity of the image to deal with the quality of the image. But you can imagine that if you are taking a film or you are capturing a photograph, you must apply some light, right? So once you apply some light, the image or the result must be better, or what kind of things you can do for it. So that's why I use another approach that keeps the maximum intensity the same to increase the quality of the image. Yes. Okay, so this is my first type of the model. It's a self-supervised learning approach with nothing better than the latter one. Okay, this is failed, but this one. Simpler, easier, lightweight, and very fast. Okay, it's just like a simple CNN convolutional neural network, but it gets a better result than the previous one. Yeah, it actually surprised me, yeah. So, how does it work? We have to look back what the Retinics theory says. Okay, so let's formulate the problem. First is this equation. can rewrite this equation 1 simply to equation 2 for optimization purpose. And later, we can use this in energy function of L hat and R hat to try to formulate the optimized function or target function to train our model, right? Where the phi and the psi are the regularization terms or functions to tell or teach the model to learn some domain knowledge from human, yes. So the problem is how to minimize this energy function so that the reconstructed image will be as close as possible to the source image. Yes. In our approach, the regularization functions are as follows. The phi one is the sum of two terms. The first one, is the difference, the Frobenius norm of the illuminance and the maximum intensity of the source image. And the second one is smoothness aware likelihood or something called similarity of the image, source image and the illuminance image. So that the illuminance image will be similar to the source one. Yes. Okay, and the second regularization function is the psi, and its similarity index for the reconstructed image L hat and R hat and the source image I, yes. Okay, so the problem is reformulated by these two optimized functions. Yeah, the previous one is like this. Is a whole one, but I separate it into two functions. The first one is for training the decomposition model, and the second one is for training the relighting model. Okay. So how do we train the model? First, I prepare a decomposition model that with the parameter set theta. And then I fed the normal images into the model so that it can return the illuminance and the reflectance of the normal light image. And then I optimize it with the equation 7 that mentioned before. And then we prepare the second one and pass or share the parameter set to the second model. And train again, but with lower light images to get the lower version of the reflectance and illuminance. And later on, we enter the relighting phase to make the prediction of the relighting and help this with the illumination through the element-wise product to get the final result. And so this is a training loop that we continue doing. Okay, so these some experiment parameters. Okay, nothing special. And then the results. Okay, I do different brightness levels experiments so that we can compare these things. That you can see, before and after are small, between them are slightly different, but not so much. So you cannot easily tell the difference between them. But in mathematically, it indeed decrease the brightness level, but also keep the quality of the image, so that you can feel the same thing, right? By the way, the intensity safe function is I calculate it by the mean of the intensity of the comparison and the source. Okay, enhancement. Sorry, wrong type. Okay, so I calculate it with these such formulation, so you can compare with the different results. All right, and I also compared the result with other approach. Now you can see the Uritinix is better than other, but not much better than ours. Yes. So I just directly train them and input the same input image into them to get a result. Yes. And as you can see, we get a better SSIM and PSNR, and also save a lot of energy, but in such short time. Yeah, this is my purpose. I have to apply this uh, function or method in such a real time or a high frequency application, so that it must have lower time consumption. Yes. Oh, and so the conclusion is this study introduced Max RetiNXNet, a novel self-supervised deep learning framework for image enhancement based on RetiNX theory. It effectively improves the quality of images in real time by making small changes to the human eye while conserving energy. By training the relighting model solely on low light images and enhanced normal light images, it validates the value of low light imagery as training material. And this is my reference. Thank you for your attention.
Any question?
Okay.
Thank you for your presentation. I'm just curious if you say the runtime is 20 milliseconds in the end. I'm curious, did you test it on PC or directly on a VR headset?
Actually, GPU in the PC.
Okay.
Very fast. Yeah.
Okay. Did you have any test on like directly on the VR headset, or it's too heavy, you think?
Not yet, really. Yeah,
Okay. Okay. Thank you.
Thank you.
Follow question? Okay, your method is Max RetiNXNet, and so the prototype is RetiNX. This is the third one, or what, the first one?
The first one.
The first one. Okay, so you have some improvement. You have some change from the prototype. Can you explain more about what have you changed the prototype?
Okay, so first of all, the structure. Yeah, you can see that it got much simpler than the previous one. Yeah,
Much simpler.
yeah, because the first structure I proposed is this one, but it gets very slower than the current one.
Yeah.
So yeah, because this structure is similar to the RetiNXNet that you can see here. Yeah, just two stages. One is decomposition and the second one is adjustment. So I just maybe like yeah. And then I try to simplify this structure to increase the speed of the speed of inference.
Okay.
Yes.
Okay. So your work has improvement than the prototype and some work in existing work.
Yes.
How is the overhead of your work? Overhead.
And I didn't do the different first.
Because I think so you have some improvement like as PSNR. You can show the comparison page. Comparison. Yeah.
This one.
PSNR improved, SSIM improved, energy saving improved, and the capacity improved, right?
Yes.
But I think some trade-off will occur. 你都提升，你都没有那个会产生新的一些，比方说你的架构会比较复杂。
Yes, I discussed with my advisor that why did he have a lab in the feature extraction stage, you can add a lot of layers to extract the features, but those features are too detailed for this theory. Because retinate theory is the global theory that it just divides and separate them into two, luminous and reflectant. So I don't think it's about the structure of the complexity of the structure, but the loss function or the training data you give it to train.
Okay.
Yes.
The most significant improvement is the energy saving, right?
Yes.
It's very
Oh, I
important.
can explain that more. In my approach, these function, these other approaches, they always exposure the image. So the PSNR will get a lot more higher. But I reduce all of them of the intensity with the ratio of the source image and the enhanced one. That I can reduce the intensity of the enhanced one back to the same as the source one with the ratio of the maximum intensity. Yes.
Okay. White is minus, right?
Yeah. Because I explained here that the intensity saved is calculated with this formula. That the average, average
yes.
intensity, the ratio is from the maximum intensity, but the saved intensity is calculated with the mean of the intensity.
Okay, I see.
Yeah.
Okay. Thank you. We welcome the second speaker.
Good morning, everyone. Today I'm going to talk about my topic, and our topic is efficient segmentation of OCT images for retinal layer analysis on edge device. And my advisor is Chen Kai Lu. My name is Ko Xiang Zhang. And this is my outline. I will separate about 6 parts. And first, I will talk about our introduction. And OCT is a non-invasive image, widely used in medical field, and it is especially in diagnosis of OCT disease, and it can use in many fields. And OCT use a low frequencies light source, and to measure the time delay and intensity between the light and reflection of the tissue, and the reference beam through the principles of optical interference. And this allows the multi-layer structure of the tissue can be accurately measured. And then I will talk about what is segmentation. And segmented segmentation is to classify the each pixel into the image and segment out different objects. And in segmented segmentation, each pixel is classified into a certain category, and it will distinguish different instances of same category. And for example, self-driving cars need to recognize vertical and traffic signs, and sidewalks, and other road features. And semantic segmentation can be used in a variety of applications, such as autonomous driving, meta images. And a simple example of semantic segmentation is to classification an image into two classes, like this picture is separated into background pixels and person pixels. And this is the background of our outline. And we separate into three parts. First is the real-time diagnosis applied to the medical auxiliary equipment. And second is the edge computing of challenge and opportunities. And third is the balance of accuracy and reliability. And first, semantic model can be integrated with optical coherence tomography OCT equipment for medical assistants to help doctors to diagnose their condition. And for edge computing, although edge device can often have limited compute powers, developing the lightweight models is very crucial for our device. And balance of accuracy is means maintaining high accuracy and reliability to pursue the lightweight accuracy. And it is very significant challenge for us to do in medical. And next I will talk about my proposed method. And my dataset use is HCNS dataset, healthy controls and multiple similarities dataset. And it is a dataset consists of 40 healthy controls and 21 patients with multiple stimulus. And it consists of 8 different layers and 1 background, like this picture shows. There are 8 layers in this picture. And the dataset used is 12,005 number. And the dimension we use is 128 and plus 128. And class is 9. And for retina layer, we can observe the retina nerve fiber layer and GCL, IPL, INL, and RP is the important because this is because this is and sorry, I talk about my model compare. This is my model compare. And the left is the original model, and the right is our now model. And the difference between the original model and our model is the MEU layer. I will talk about how we delete the MEU1 and to make our model better. Okay. And I will talk about FP model. FP model is separated into 1+1 convolution and 3+3 deconvolution and 1+1 L convolution. And deconvolution means bitwise convolution, and L convolution means linear convolution. And the FP bar is based on the deep separable invert bottleneck bar. And it replaces the 3+3 deconvolution into 4 subsets. And 3+3 deconvolution into 3+3 deconvolution. And it has a dielectric rate in severity 1, 2, and 4, and 8 respectively. And this is the decoder's part. Decoder's part is MEU module. Because high-level modules on the modules undergo the global average pooling operation, 1+1 convolution and without operation. Then they are multiplied with low-order features. And MEU module is the part we delete because low-level features low-level features consist of edge and texture and colors, and high-level features consist of object parts. The two features are the spatial. The two features are the part of the NEU module, and we import the low level feature. The low level feature is important as well. It is because low level feature in our part because low level features in our part is only close the axis. Yeah. And we will replace SE blocks into ECA blocks. And I will talk about why does ECA modules have a slow number of parameters to have a better result. SE blocks to ECA blocks is on the FPE module, and it is on the left and it is on the left and the final of this part. And why replace SE blocks to ECA blocks have the better result is the SE modules use two fully command layers, and it will require a large number of parameters and calculations. But ECA only use a one-dimension convolution, so it will have the less parameters of the model. And so we replace this part to ECA block to have a better result in our module. And the matrix we use is dice coefficient for our indicator. And this is the result of our part. The result, this is our hardware and specification. And we use is actually i7-12700, our CPU. And the graphical use is 3090 type. And this is the application test, the NEU conversion. We delete the NEU module. We separately delete NEU module 1 and NEU module 2. And in this result, it shows delete NEU module 2 have a better result. And in this module, this is SE module and ECA module's performance. And we delete ECA, we use add SE and add ECA module and delete NEU2 to run our method. Because delete NEU2 is better, so we use it to try. And you can see the parameters is lower than the follow SE module, ECA module. Because ECA is only one by one convolution. I talk, but the force is a little higher. But our device want to use on the edge device and like Raspberry Pi. So we balance and we know our module needs parameter is less. So it is the important than the force. So we use this to run. Because if we don't change this part, our module may not be able to run on the Raspberry Pi. And this is the HCS SE module and ECA module. Compare test coefficient. And this is FPE, SE, and ECA. And you can see the NFL, UCL, and so on is better than the SE module. And this is a result of our method. And you can see our method has the fewer carrots and the fewer flux. Then the PSP net, ESE net, and ESP net, and the recently used LOCT SIG net. And this is other result of our exchange size coefficient. It shows the overall accuracy of our module was 92.06% when classified 8 layers. And this is the conclusion. We proposed a lightweight module for classified 8 layers using the HCNS dataset. And it is indeed to more accuracy than exists technology and reduce number of parameters. And it is beneficial for use in lightweight device. Due to our change, we change it to on our lightweight device. And compared to LLCT, it has 1.1 improvement of OS and 0.5 improvement of GCL and IPO, and 0.4 to 6.5% improvement on RPE. And the force and parameters also have some improvement. It shows on this picture. And this is the future world. We will focus on using more data sets to train the model's generalization ability and improve the accuracy through the federated learning. It is a method. Our module's ability to handle the multiple data. It can open new applications in other fields. Maybe we can use in car detection or some other technology. And this is a reference. Thank you for your watching.
Any question? Member of Professor Liu. Then, this is your research topic. Do you have any question? Okay, can you go back to page 20? 20. Okay. The existing work you compare just like 3, 4, 5. The five existing work is from your lab or not?
And it's from my lab.
So 3, 4, 5, 6, 7.
1, 2, 3, 4, 5. Yes.
Okay, so you compare your work. You compare your work with the existing work of your lab.
Yes.
Okay. Which one is the newest?
Newest is LOCDC.
OCT.
And it is 2021.
2021.
Okay.
Okay. Because I am not expert of this region, so I cannot figure out what is the most significant contribution of your work from the others.
The contribution I think is the parents, because the original parents we use is based on the FPNet, and the parents is 0.114, and our method used and to reduce the parents and reduce the flux to make it better on the edge device, because our achievement is to make this module to run on our Raspberry Pi, and it can run on Raspberry Pi. We test.
The current from 46 2 years 0.08, so it reduced very much.
Yes.
So can it be improved more?
Improve to Raspberry Pi. Improve.
Improve. because you compare two parts. One is the primary, and the second is float, right?
Yes.
So can they both improve more?
I think it can improve more, but I need to do some change on our model. So can try. Yes.
Okay. No further question. Okay, thank you.
Thank you.
Hello everyone. Today I'm going to talk about the topic of resource creation approach based on machine learning to ensure QoS in 5G heterogeneous network comprising macrocell and femtocells. And my name is William Chen, and my advisor is Jiabin Wang. And this is my outline. I first will make some introduction and the background, and next I will talk my simulation and the conclusion. Final is the reference. And for the introduction, due to the significant increase in the data traffic in mobile communication in recent years, the traditional serial network architecture with macrocell will not be able to burden a large amount of model flow data in the future. In order to solve the above problems, the global technique operators began to seek the new technique of the wireless network access architecture. For example, hybrid deployment of macro and femto-based stations were built to reduce overall operating cost. In the future, small cell is regarded as a key device for improved transmission capacity and deep network coverage in the 5G mobile broadband network architecture. And in the crowded place, a large number of users enter and exist in short time, and the throughput of the system is greatly increased, and these places are called hotspots. In order to solve this problem and reduce macrocell burden, it is necessary to build a large number of small cells in a small area. In some area, due to the influence of large buildings or natural shelters, there are some weak signal area within macrocell's coverage area. In order to make up for the lack of macrocell coverage, it is necessary to construct a small number of small cells in these locations. And this is my research motivation. In the heterogeneous network environment, the purpose adding a small base station is to increase overall transmission efficiency. But because the macrocell's transmission power is much larger than the other small cells, so the users is in the several service area are greatly distributed. Small cell may be also set up by users. If there is no overall specification, the problem of the same layer channel interference will occur, and the overall small base station network transmission performance will be reduced. In the event of the efficiency cannot be effectively improved, the purpose of the deploying small cell is lost. This study, my study is focused on the power control and resource allocation of macrocell and small cell to solve the interference problem and to improve the overall network rate. the wireless network environment problem after 3GPP release 10, we call R10, mostly revolved around the heterogeneous network architecture. We can add some lower power, such like picocell or femtocell, collectively called as a small cell, to the traditional microcell. We can look at the lower table. This is about the type of the base and the transmit and the coverage. In the recent year, AI is also considered the method can solve this problem. Reinforcement learning in the field of machine learning is also the highest effective approach to solve this problem. We will talk about the RLO method later. The related work, reinforcement learning aims to interact with unknown environment of our system and find an optimal solution through this interaction problem. It can be divided into the centralized and the centralized approach. In our first reference, it is being widely used across multiple scenarios, particularly in the field of the communication for resource allocation, as seen in the number 2 to number 4 reference. The most crucial aspect of the RLO lie into setting the reward function. The appropriateness direct impact the result. Different in the power allocation based on different reward function can be observed in the number 5 to number 8 reference. The difference between these two is two reference is used independent learning, and the other two is for the cooperation learning. And now we'll talk about our background. Compared to 4G, the global deployment of the 5G network has several significant. According to the report by the General Service Administration in the United States as the 2021, 100 of the company and 61 countries worldwide has begun to use the 5G network service. With the development of the 5G network, the release of the 3GPP standard release 16th version into metro industrial such as autonomous vehicle and industrial network, smart logistics, and telemedicine. The development is expected to foster and the growth of related industrial and leading the great prosperity. The 5G wireless network is, first we'll talk about most important is 5G NR-U. 3GPP release 16 introduced the two operating model. First is standalone and the next is license access. It reserved 5 GHz and 6 GHz frequency band for the use without license. This mark is first time that 3GPP has independently defined cellular technology, and such combinations are expected to see significant use in the 5G domain. And now, next we will talk about the femtocell development. We will talk about this above the small cell, and this is about the small cell, a part of small cell. And first of all, we will talk about the femtocell access control. There are three features. The first one is open subscribe group, and this means all users can access the service provided by the FBS system. But it will make some problem because the privacy and the security will concern. Next one is closed subscribe group. Surveys are only offered to authorized users. This can ensure the protection of users' privacy and the security. And the third one is hybrid subscribe group. This bandwidth is provided to the authorized CSG users, while it also gives some bandwidth for that non-rejection users. And next is self-organization network. This also has three characteristics. And the first one is self-configuration, and the second one is self-optimization, and the third one is self-healing. And respectively, it can first can automatically configure the relevant parameters based on the environment and user's need, without requiring manual intervention. And optimization is observing the current network condition of the femtocell and the various data from the users. And self-healing is the femtocell system is capable to automatically inspecting and identifying faults or issues when encountered some issues. And the third one is the spectrum allocation. These two spectrum allocation is the first one is shared spectrum reuse. FBS and MBS can simultaneously use the partial or all frequency band. They use the same band. And second one is splitting spectrum reuse. The FBS and MBS operating on their respective frequency band. And these two has their own advantage and their disadvantage. And the final one is the interference environment. There are two kinds of interference environment. The first one is COTIER. When users are on the different layer, for example, the macrocell and the femtocell, they will. This is from the upper layer to interference the lower layer. And the next one is COTIER interference. The interference is occurred on the same layer base, just like the femtocell can interference their neighbor femtocell. And next is my simulation environment. And for my simulation of the heterogeneous network, dense network scenario was modeled. In this environment, we will it is considered of the one macro base station we call MBS, and the macro user equipment MUE, and the 16 FBS and 16 FUE. We should consider about the link between the MBS and MUE, as well as the link path consumption model between FBS and the service FUE. This can be derived from the following equation. And also the link between FBS and MUE, as well as the link path loss between each FBS and FUE of other FBS. And next we will focus on the power allocation in the downlink of heterogeneous network, and find that the density is the most significant influence factor. Excessive network density can lead to the decrease in overall performance. In the downlink, MUE users receive signal from MUE as well as the interference and thermal noise from FPS. Therefore, we can calculate the signal to interference plus noise ratio, we call SINR, for FUE as the following equation. Similarly, the SINR for FUE can be calculated like the following equation. And the next, the channel parameters are assumed to be unknown to the FPS, which is reasonable in practice as the information can be fed back to small base station via the backhaul network. Finally, the capacity normalization of all users' device can be obtained from the following equation. And that is all my parameter we'll use in my simulations. And next, I will talk about my reinforcement learning setting. And in RL, I will use the Q-learning. And Q-learning, next I will talk about the setting of my actions, state, and reverse. And then actions, we will select the transmission power for each FPS from the set, the A1, A2 until the N, which their range will cover from the power, from the minimum power to the maximum power, and we will talk about it later. Yeah, from -10 to 25, and this is my and we will make the every step is the same from A1 to N. So this called 间隔 will be sent. In the next state, we can use to represent the current position status of the FPS. We select state based on the current position of the FPS related to the MVS and FPS related to MUE. And we'll define the two parameters. First one is the distance, and is the MVS distance. We will see the ring from the R1. This on the figure is the red ring, and the next is the distance and MUE, and this is the last one is the blue ring, and the next one is the red ring. It's called this is we see the state to represent the state of the FPS. And the next is the rewards. We have to meet the user quality of the service in the requirement. It is necessary to consider the portion of the users whose capacity fall below to the threshold and require for QoS certification. If the capacity is below the threshold, the penalty will apply. In order to maximize the total user capacity of the existing network, the larger reward are given to the users with the greater capacity. And we can see the lower equation is our setting, right? And next is our result. And we can see the first figure on the upper left-hand side. We can see all the MUE capacity are all maintained above the threshold, and the right-hand side we can see the FUE's capacity with the FPS number increase. It can maximum maintain until the 7 FPS number to put it into the environment. And then the third figure is the sum capacity of the FUE, and the next one is the MUE capacity plus the sum capacity of the FUE. And final result we will compare to the other reference their setting of the reward function. And we can see the first picture we in our proved reward function we have the head of the 8 of the reference. We can all maintain on the threshold, but the reference of A it cannot it all below the threshold. Despite of it has the more capacity of the FUE, but we look at the number 9 reference at the FUE capacity it all below the threshold, and we can see the result that we have the better balance of the all including MUE capacity and FUE capacity. We can maintain the balance of the two result. Yeah. And that's our conclusion that it's using our algorithm we provide can ensure that the capacity of the MUE increase to above the threshold, and while the total capacity of the FUE does not decrease significantly. Thus, we achieve the higher level of the balance. And in the future, we can explore using the different reward function or other algorithm to reduce the interference and improve the capacity. Yeah. And these are reference. Thanks for listening.
Okay, thank you.
Sorry, can I know why you use Q-learning in this model?
Q-learning is of policy strategy for the reinforcement learning, and why I choose the Q-learning because the exploring is the better. It can explore the better result for our training. Yes, it has the better exploring 能力，it has the 它有比较好的探索能力。Yeah.
Okay, thanks.
Do you try another method to deal with the interference problem?
Traditionally, we use the game theory, and that is not the good way to use because nowadays we have AI, so we try to use the reinforcement learning to deal with the problem. We also try the other AI way to reduce the interference, but this way is the better way. So yes.
Okay, thank you. Next one.
Good morning, everyone. I'm Yujin Luo, and my advisor is Zhen Hongling. Today I'm going to introduce my paper called Tiny Seeker, a network for seeking tiny and fast-moving objects based on a symmetric UNet. this is my outline. First, I will talk about the reason why we start to build this model and the method we apply to conquer the problem. Then I'll show the details of our structure and results table. Finally, demonstrate the results in video and make a conclusion. So nowadays, AI has been applied on many fields, and sport is one of them. FIFA World Cup held in Qatar 2 years ago is one of the best examples. However, the technique they use costs too high for normal people like us, for the amateur or school team, even for some countries. It's not an affordable price. But I think we all agree that the purpose of every invention is trying to make the world better and allow everyone can use it eventually. So in our paper, we focus on badminton and try to build a model that can be used by anyone to easily track the ball. But badminton itself is not the type that can easily recognize when the game started, even by our own eyes. It's tiny and fast-moving. Well, high speed, according to the latest news, is 565 km/h, hit by a player from India a few months ago. Such a high-speed object is hardly to see clearly in one frame. As you can see in these three photos, in picture A, maybe we can find badminton by the movement of the player. But in picture B, it's almost overlapped with the logo on the ground. And not to mention in picture C, it looks like an UFO flying through the player's face. And the worst thing is, it's all white. That means it doesn't have many features. This makes us harder to aim it through traditional object detection like YOLO family. So if you expect to locate the badminton, you must refer to pattern it moves. For example, the badminton in picture C is what I'm trying to find, but I can find it directly through the picture. Therefore, I need picture A, picture B, and picture D to help me target it. That's why we take 4 consecutive color images as the input of our model. So with input data ready, we can apply TinySeeker to locate the badminton. TinySeeker is a model based on UNet. It is mainly composed of 7 layers, including 4 encoders and 3 decoders shaped into an asymmetric structure, which means the last decoder block of UNet is eliminated. This design aims to reduce computation requirements while maintaining a comparable level of precision, as evaluated by the F1 score. At first, all the consecutive images will be resized to 640 by 320, then project to the encoder block. As mentioned before, because badminton lacks features and the shuttlecock in the frame might be represented by just a few pixels. Therefore, TinySeeker introduces an innovative approach by predicting the likelihood of the object presence for each output pixel. This results in the generation of an output probability map, also known as heat map. The approach represents a significant departure from conventional object detection frameworks, which typically predict the object coordinates along with its width and height. To explore more details of the architecture in TinySeeker, here I'm going to introduce what is inside the encoder and decoder blocks. In each encoder block, 1 3x3 downsample layer and 3 convolutional layers are included. As for decoder block, we apply 1 4x4 deconvolutional layer to do the upsample and also connect it to 3 convolutional layers. To provide a comprehensive understanding of the TinySeeker architecture, we present both the symmetric and asymmetric UNet models in the figure below. We emphasize the distinctions between these structures and emphasize the advantage of TinySeeker. Figure A showcases the symmetric UNet model, which takes 4 consecutive color image frames as input and produces an output heat map of the same width and height as the input. The heat map has a feature dimension of 1, and the model output values are transformed to fall within the range of 0 to 1 using a sigmoid activation function. In contrast, Figure B depicts the architecture of TinySeeker, which maintains the same input dimension dimensions as symmetric one, but differs in terms of the output. In TinySeeker, the height and width of the output he mapped are halved compared to the original dimensions. This design shows significantly reduces computational requirements while retaining the same input resolution. In Figure C, we present an inverted configuration compared to TinySeeker. This configuration features a low resolution input and a high resolution output. We propose architectures B and C to evaluate whether input features or output resolution are more critical in reducing computational demands. It is important to consider the potential limitations of each approach. Insufficient input resolution may lead to the target object disappearing or being poorly represented. On the other hand, inadequate output resolution may result in coarse predictions, leading to offset errors. These considerations underscore the importance of striking a balance between input resolution, output resolution, and computational efficiency in the design of TinySeeker. Here are two tables indicating the performance of TinySeeker. First, look at the table on the right side. It shows that symmetric UNet slightly outperforms TinySeeker in terms of F1 score, which is combined measure of precision and recall. The difference in the best F1 scores between the two models is approximately 3%. However, TinySeeker exhibits an average training time that is around 6% faster than symmetric UNet. In table on the left side, the computational complexity of the models is presented, indicating that TinySeeker demonstrates a 26% reduction in computational demands compared to the symmetric UNet. This reduction in computational requirements is significant, considering that the F1 score is only slightly lower. This trade-off between computational efficiency and performance represents a favorable compromise. Then we look back to the table on the right side and analyze it further. It is evident that TinySeeker achieves higher recall, while the symmetric UNet demonstrates higher precision. This difference can be attributed to the insufficient output resolution of TinySeeker. When the predicted position in the low resolution output image has a difference of just 1 pixel, the potential location of the badminton shuttlecock in the original image can vary by several pixels. This discrepancy can accumulate during the restoration process, leading to a degradation in precision. Future research could focus on addressing this issue to improve the overall performance of TinySeeker. Now let's see the demo video. So in this video, TinySeeker target on the badminton as a red spot. We can see it track well in professional games. And TinySeeker can also apply on regular practice courts. In this video, it also shows our model not just target one, but target all the badmintons on the court. In conclusion, we provide an asymmetric model that can localize the shuttlecocks without huge computation and still balance between accuracy and computational efficiency. Finally, it can locate badminton in video shot by normal camera, which is consistent with what I mentioned in the beginning, to allow everyone to use the technique. And that's all of my report. Thank you.
Any question? No? This was really interesting. No question? Okay, great.
Thank you for your presentation. It's a nice work and you got nice results. I'm curious, you have a time-related problem, right? and you solve it by giving as inputs to your unit 4 different images that are consecutive time steps, right?
Yeah.
Yeah. So I'm curious, why don't you use some specific network like LSTM or something like this for this kind of problem?
Because if you use, for example, using a dimension of t, which is time, and use convolutional 3D, it's not efficiency. If you compare it to the one layer of convolution 3D and 2D, it may be 5 times faster when using the 2D one. And we also, because our baseline use the this one, symmetric UNet, and it's called TrackNet. It's proposed by National Jiao Tong University, and they also use it as the badminton tracker. So we compare to them and using the similar structure with them.
Okay, thank you.
I remember this one as we the best work in the computation.
Yes.
This one, right?
Yes.
Because I'm emphasized by this work because it can apply to the game such that you showed the example and such that table tennis.
Now we use it on the soccer.
Soccer.
Yeah, on soccer game, but it's not really good because in the soccer game the camera will move, so the features will not weird.
The space will be smaller.
Yes, but if the camera, you just sit there and you don't move the camera, it can detect it well. But when the camera is moving, the accuracy is not that well. So we are still fixing this problem.
So table tennis is
Yeah, if the
it's a
table
good
tennis is-
example. Okay. Because I'm emphasized by this work because I think it's very it is very applicable. That you can use this work for many exercises. And this is your lab from your lab first proposal.
Yes, this is my first.
Okay, great. Okay, thank you. We welcome the next and the next.
Hello everyone, my name is Liu Yushen and I'm Professor Extension Head. The topic of my report is design of aeroplane variable gain profile. This is my outline. First, I will discuss the background and motivation, followed by the preliminary and architecture, complete circuit and some electrical design and impedance mesh components for this amplifier. Then I will present simulation and measurement results and finally conclude. Let's start with background and motivation. Generally, signal processing is carried out at lower frequencies because low frequency circuits do not need to consider additional electromagnetic effects. However, in wireless communication systems, in order to effectively transmit signals, it is necessary to increase the frequency of the signal to be transmitted signal to be transmitted to gigabit to there are radio frequency circuits that specifically deal with frequencies above gigahertz. With the advancement of technologies, it has developed to the fifth generation of mobile communication. The main frequency bands are the 5 into sub-6 gigahertz and millimeter waves to growth of frequency range. The millimeter wave is frequency band that will continue to be researched in the future because it can avoid congested low frequency bands and use ultra large bandwidth to increase the transmission data rate. And its advantages are short wavelength and strong penetrating ability. Disadvantages are high directivity in a high frequency band. The transceiver system is composed of multiple circuits, including low noise amplifier, mixer, power amplifier, variable amplifier, filter, and so on. However, because the strength of the received signal can vary in different situations, it is necessary to amplify and adjust the signal to ensure an appropriate signal level enters the subsequent processing stage. Therefore, variable gain amplifiers play an indispensable role in both transmitters and receivers. Next, I will introduce the architecture of the variable gain amplifier. The diagram illustrates the circuit architecture to meet the requirements of the subsequent systems, including high gain, low noise, and variable gain specifications. This design will initially use a two-stage amplifier configuration. The first stage will focus on low noise amplification, while the second stage will emphasize high gain and output power. The two-stage architecture of this VGA will choose between the common source configuration and the voltage buffer configuration. Ultimately, after analysis based on maximum gain stability and minimum noise figure, the common source configuration offers higher gain and lower noise. However, due to its lower stability, it is less easily matched and consumes more area. Therefore, in the overall architecture, the first stage will use an inverter buffer, while the second stage will use the common source configuration to provide higher output power. Next, I will introduce the complete architecture of the variable gain amplifier and its components, along with the advanced design considerations. Here is the overall circuit diagram of the variable gain amplifier, which uses a differential input and output configuration. It provided a current path through the current mirror structure with series capacitors between the two stages for matching and separate the direct current path of the first and second stage. The current control architecture controls the size of VC, which is the VGS of the transistor, to vary the current following solar transistor, thus achieving variable gain. The diagram shows the basic structure of the current mirror. On the formula, we can see that the current ratio of N1 to N2 is related to the size ratio of the two transistors. For effective amplification, the amplified current ID must be equal to the DC value of the differential amplifier, so that it operates at the same operating point.
In addition to the above considerations, this current mirror structure carries over current to avoid transistor breakdown due to excessive current. The length of the two transistors in the current mirror structure has been increased from the minimum process size of 0.18 micrometer to 0.35 micrometer. The primary purpose of a variable gain as the length jet is to adjust its gain according to requirements, matching the specifications and variable range needed for different system architecture. Current steering is the current extraction structure of this circuit. Simply put, exchange the current state by changing the control voltage, thereby changing the overall gain. In this control architecture, which changes size, area, and bias sticks to maximize the range of variable gain, the body bias is adjusted to increase the current. As shown in the equation, if the bias at the body increases, it will decrease the social voltage of the transistor. According to the transistor current formula, if the social voltage decreases, the current following through the transistor will increase accordingly, enhancing its current extraction capability. In this amplifier architecture, more current will be drawn away, reducing the minimum gain and maximizing the range of gain control range under limited conditions. In radio frequency systems, signals are transmitted as electromagnetic waves. During signal transmission in the system, incident waves, reflect waves, and transmit waves are generated. We can use scattering parameters to describe the characteristics of these signals. In most radio frequency circuits, if the reflected signal is too large, it can lead to reduced gain, increased noise, waveform distortion, and other issues. Therefore, in circuit design, matching network and added at the input and output to convert the impedance to 50 ohms, achieving impedance match. The input match of this circuit consists of a parallel inductor and a series capacitor. The 3D model of these two passive components is shown in the diagram. By doing the corresponding components in the simulation software and incorporating the software-generated characteristic files into the circuit, the formula can better approximate the actual chip conditions. The output matching also consists of a parallel inductor and a series capacitor. However, unlike the input match, the two inductors in this case can be combined. Use a special drawing technique to minimize the area. Finally, there is interstage match. As the name implies, the impedance in between two stages cannot be perfectly continuous. So impedance matching is also necessary. This matching is composed of a capacitor, which in addition to its matching function, also separates the bias of the two stages, allowing the gate terminal of the second stage to have an impedance bias. Next, I will introduce simulation and measurement results. Before showing the characteristic results, I would like to show you the setup image of the chip during in the image of the part of the left is for input, the one on the right is for output, and the top is for biasing the transistor. It can be seen that the change in simulation and measurement are similar. Unfortunately, the gain did not maintain its original simulated level at high frequencies, resulting in narrower bandwidth in the measurement than in the simulation. The top graph shows the scattering parameters for different control voltage levels. The bottom left graph shows the gain for different control voltage levels. The bottom right graph shows a variable gain range for different body bias voltages. Interestingly, compared to the simulation, the measured minimum gain is actually negative, and the measured variable gain range is more than twice that of the simulation. It is speculated that there may have been a design oversight in the layout current extraction structure leading to discrepancy between the measured and simulated value. This graph shows the noise figure and power performance at different control voltage. It can be seen that the power performance for large signals is not significantly different from the simulation. Next, I will show the layout diagram and the actual chip image. The layout size of the chip is 0.87 millimeters by 0.72 millimeters. This is a photo of a chip during measurement with the black areas indicating the input, output, and bias port. Finally, is the conclusion. Okay, this is compared with other published literature. It can be seen that my design has relatively low noise and a good variable gain range. However, due to its differential architecture, it consumes more power and occupies a large area, which areas are improvements. This is my reference. Thank you for listening.
Any question? This is Eva.
Yeah.
Okay. So the simulation result and the measurement result is really different. You see? So it's okay. So it didn't need to help out here.
It's enough to use
Okay.
in our budget.
Thank you. Okay, that's all.
现在还在念库嘛，那人家欣姐行政干事进来也是有办采购案的，然后也是兢兢业业在弄这个。
没关系，你只要跟你的研究主题相关的就好，因为我知道有些同学